portal for high precision atomic data computation. Could you please introduce yourselves and please begin? Thank you.
Sure. I will start by sharing my screen. Is it coming through okay?
Yes, it is.
Okay. Hello, everyone. It's a pleasure to be presenting here today. My name is Parinos Barakshan. I'm a PhD candidate and research assistant at University of Delaware, and I'm presenting on behalf of my colleagues that are enlisted here. Today's presentation is about Atom Portal that presents high precision atomic data and computation. Let me quickly introduce you to the team. It's an interdisciplinary research project. We have people from physics department, computer engineering departments, and here's a list of their names and affiliations. Here's the agenda. I would present you to the problem and our solution to it, and then features developed in version 2 of the portal would be discussed. Upcoming features would be mentioned. Some of the challenges we faced are explained, and at the end, some of the lessons learned from the collaboration are shared with you. Well, in many applications, ranging from studies of fundamental physics interactions to the development of future technologies, accurate atomic theory is required for the design and interpretation of experiments. Atomic theory is a theory of the nature of matter in which we are talking about elements, their electron states, and some important properties of those elements, like, for example, matrix elements and polarizabilities, for example, which I would explain later on each of these properties. The fact is that experimental measurement of the properties of these elements is often infeasible, if not impossible. That's why we decided to create an online portal that provides high precision atomic data derived from computationally intensive calculations performed on a growing number of atoms and ions that would be very challenging to obtain on demand. Codes are capable of calculating a very broad range of atomic properties to answer the scientific needs of atomic, plasma, and astrophysicist communities. Data are calculated using a high precision state-of-the-art linearized coupled clustered method, which is a numerical technique used for describing many body systems. And estimated uncertainties are included in all values, and where available, experimental results are provided with references. Let's talk a little bit about some of the developed web pages and explain their functionality to get a better view of the project. This is the front view of the project. On version 2, user interface is adopted based on the user feedback. Atomic properties of 25 elements are displayed. The portal provides information on properties like matrix elements, transition rates, scalar and dynamic polarizabilities, energies, hyperfine constants, nuclear data, and atomic data for atoms and ions that are enlisted here. I don't really expect you to know these properties. I just use this term so that you can get an idea of the number of properties that have been calculated and presented in this version of the website. And I'm going to present 2 properties of these elements today, so I'm going to explain it a little bit. The first one is called matrix element. The matrix element property gives information about whether a transition from an initial to final state is possible, and if so, the strengths of that transition. When you land on this page, all the electron states of the element, in this case sodium, appear. You can simply click on a state to get all available matrix elements for this specific state. Each row indicates the initial state, which is the state you have selected, the final state, and the strengths of the transition that we call matrix element property. The user can also print or download the Excel file to get the table information. The other property is called polarizability, which is a measure of how easily an electron cloud is distorted by an electric field. You can simply click on a state button, for example, 3s half, to see a dynamic polarizability plot for this state that you can see in the middle of the page. Then you can use like the sliders or plot tools to rescale the graph. You can also save the graph or download the data file used to plot the graph. We have created web pages for the other properties that I mentioned earlier, but I won't go through them for the sake of keeping this presentation short, but the other web pages are following almost the same structure. Now let's talk about what we have in mind to release in future versions. In future versions, atomic computational codes could be released, it would be released, and in case you want to try to generate data on your side, you can use them. More elements and properties will be added to the website. We are talking about up to 100 atoms and ions. And then to facilitate updating the pages and avoid human error, we are automating the creation of all the web pages. In addition to that, we seek community input to guide future releases. And one of the reasons we are here today is to get feedback from Science Gateway's community. Here's the link to provide feedback to us. So in case you have anything in mind that we can provide to you, simply bring it up. Some of the implementation challenges we had are related to automating web page creation. There are two main reasons we decided to do the automation. First, we didn't want any manual changes to the data to happen. And second, we wanted to make the creation of web pages for all newly introduced elements as easy as possible, even for non-experts. So we wrote Python scripts to read data from CSV formatted data files and create the related web pages. The next challenge was the display of the denominations for electron states, such as the one you can see on the screen, for which LaTeX inserts are generated. As I mentioned earlier, we are getting CSV files as data inputs. CSV files don't have formatting in them included. So we did a mapping between the states presented in CSV file and the LaTeX formula generated to each state, related to each state. Then the next challenge was about creating graphs for polarizability property. We had specific demands like rescaling the graph, saving the graph, showing the mouse position on the graph while hovering over it, for which we took advantage of the bokeh visualization library. As I mentioned earlier, this is an interdisciplinary project, and the team consists of physicists and computer scientists contributing to the design of the portal, both from a physics and software engineering perspective, applying best practices for collaboration and software design. Some of the lessons learned in this collaboration are we need to set expectations early in the process, discuss the roles, the responsibility, who's going to take care of what, and then discuss the technologies that would be used in the project. What are the programming languages we are going to use? Is there any reason to use a database, or what's the underneath architecture? Discuss what it would take to work together better to advance the shared goal, which tools to use for the sake of collaboration, how the meetings should be set, all those. The other point is an important one that I cannot emphasize this point enough, because it's really helped us save lots of time. And it's about automating the process whenever you can to remove all these repetitive tasks. The last point is about considering community feedback in design decisions for the purpose of making the project as user-friendly as possible, especially in case of multidisciplinary projects. That's all I had for today. Thanks for your patience and listening to me. I've included the link to the portal and the link to provide feedback as well. If you have any questions, we still have a few minutes to discuss it.
If there are any questions, you can unmute and ask them or put them into the chat.
So Fernández, I would have a question.
Sure.
So you have really great data in your Science Gateway there, and so how have you seen how yeah, people like to share the data? Do they find it easy to upload? You can contact them and they're happy, you know, to provide part of the data, half of the data, you know, all this around sharing data. Are they okay with it, or do they feel like, oh, I have to do it after publication? So how is the reaction of the researchers there?
Well, we got some data from community, and then they were willing to share it with us and get it published. So we used it in our portal, but I'm not aware of all those challenges that you mentioned to me, Sandra, because those data are going to be passed to the physics department just to make sure everything makes sense. And then they are passed to us in order to put it on the website. So I can kind of direct you to the person who's called Mariana Safronova, and she would be able to answer your questions in that regard better.
Thank you. Yeah, I know every area is also different with data sharing, so I was only interested. Yeah. Okay. Thank you for a great talk.
Thank you.
Thank you, Fernández. We'll go ahead to the next one. Next up is Portal for High. Oh, wait a minute. Sorry, no, the next one is the release of a Science Gateway for climate data in Hawaii. Sean, go ahead.
Okay, can you hear me all right?
Yes.
Yes,
okay,
loud
great.
and clear.
All right, thanks. My name is Sean Cleveland. I'm a cyber infrastructure research scientist for the University of Hawaii, and I'm going to talk about the Hawaii Climate Data Portal and the recent release we just had. So today I'll cover some of the background. How did we get to where we are? What does this portal do? How did we roll it out, and how are things currently going? So a little bit of background. The Climate Data Portal kind of came out of another project, which was called the Ikiwai. That means knowledge of water in Hawaiian. And so this is a part of our Hawaii EPSCoR project that we've been working on for the last 6 years. And the whole idea was building a platform that could bring data models, computation, analysis, visualization, kind of into one sort of place, one platform to enable simpler access to data tools for our researchers, our water managers, our community, so that they can make better decisions. And so what came out of that was a number of different tools built off of the same platform. So different visualization, decision support tools, ways researchers can collaborate, share data, publish data, do computation, and that sort of thing. But this precipitation mapping tool is what the Climate Data Portal evolved out of. So we work with the researchers who were the folks behind that to bring this Climate Data Portal to life here. So some of the features that this thing they wanted in this was discovery and serving data products, providing interactive tools to explore and visualize the data, generating monthly and data climate map products, which was actually prior to this work, being able to create a rainfall map product could take months to, sometimes a year, depending on how, what access you had to the data and things like that, and your knowledge of the different things. So now it's done daily, and people can just, do it in a couple of seconds with this tool. And the final thing was to provide resources related to climate in the state of Hawaii, because we're kind of lacking something like that is kind of available on the mainland. So let's see. How we built this was on kind of an ecosystem of open source, previous work from some of our other NSF projects in this Ikiwai project, and then national and local resources. And so in particular, we leveraged TAPIS. So that's a open source scientific gateway kind of framework that we collaborate with the Texas Advanced Computing Center on. So generally, it's a whole framework to support science, domain agnostic. You don't have to stand it up yourself. It's hosted elsewhere, or you can host it yourself if you want. Has a bunch of tools to enable collaboration to accelerate analysis and discovery. More technically, TAPIS is a set of microservice APIs with authentication, authorization, databases to persist data that you want, or any actions that you would take within the system, as well as being able to handle computational workflows, data movement, all that sort of stuff. And as I said, hosted, the services are hosted somewhere else. So you can build on top of it or leverage some other tools I'll just discuss. But basically right now, it's powering research for over 51,000 researchers across 23 kind of different tenant groups, and then over 15 gateways. And so we leverage this for the EKY gateway, and we're also leveraging this for the climate data portal. So how do researchers use TAPIS, and how do we use it in the climate data portal? Since it's REST APIs, you can use curl. There's command line interfaces. There's also software SDKs. And so we have 3 gateways at the University of Hawaii now that we use the Python SDKs, as well as some JavaScript, React SDKs and things like that. And then we'll have other folks who are also interested. Some third-party developers are interested in the data and some of the functionalities in the APIs. And so this is the other way they'll leverage these things. So, so the climate data portal here, one of the things I talked about these data products. And so there's these workflows that have to be enabled in order to be able to generate these products in sort of real time. So being able to get daily rainfall or daily temperature products, there's a number of steps that have to happen. So being able to acquire data from a number of different sources, from loggers that are in Hawaii, to data from NASA, data from the National Weather Service and NOAA. Then you have to apply some different techniques to do some QA/QC. So they have some machine learning and gap filling techniques that Matt Lucas, Ryan Longman, and Thomas Chambaluca developed to do this QA/QC and gap filling and aggregate these data products, and then generate these interpolated monthly maps so that we get these products sort of in the end. So there was a lot of steps here that were developed by these domain scientists. And so some of the work that we did with TAPIS was to help containerize these workflows so that we can make them portable to different resources, say in Jetstream or in the TAPIS cloud itself, that can run containers. And then we sort of automated this whole thing with some of the workflow things that are part of TAPIS for being able to run cron containers within the actor service here, so that every day we can fetch input data, fetch data from the climate data portal that we need to reference for today's data, or if you're doing monthly, you need to fetch the last month's worth of data collection, do the analysis, and then push things back into the portal and annotate those sorts of things. And so this is something that we kind of all rolled out that's in the portal and actively running to make these products possible. So leading up to the release, we did all that work to develop the products that need to happen and need to be generated every day and every month. But then there was all the we did all the development, and then leading up to the release, there was all these things that we had to do to make it successful and reach out to the community. So big thanks to Michelle Cho and Maria Duman-Lang for all their logistics, communication, and cat wrangling for making this possible. We originally intended to release the portal in the fall of 2021, but we kind of held off to make sure we had some additional products, some temperature products, because originally it was just going to be rainfall, but then they said, well, temperature we could achieve, and it would be great to have rainfall and temperature, so we waited. But anyway, 3 months prior to our kind of release, we began marketing to our stakeholders and communities through email communications, at other events, through flyers and things like that, to kind of get the people excited. Then 2 months we started, registration for the event. We ended up with over 275 registrations. So our capacity was 300. So we were concerned we would hit capacity for the number of people we'd be able to host in Zoom. Then a month out, we ensured that we could track all of our metrics, because we wanted to be, see how popular this tool would actually be with how much buzz was generated. And then a week before, we were able to get our tutorial materials ready, so that it would, if we had a lot of people hit the tool, but they weren't able to attend some of our demo, they would know how to use it. And then we were still doing some minor updates to the UI the day before. People would find things that are like, this isn't labeled right, and such. So right up to the last point, we were continuing to make updates. And then it turns out the local press got a hold of our rollout, and they released our link a little early before our release, but luckily we were ready. So that was exciting. But come the day of the rollout, we had a 2-hour online event in which we had 6 different presentations and a full demo of the product. And we had over 225 attendees on Zoom that were very interested in asking questions, and a lot of them stayed for the full time. And so what we ended up releasing was this tool that enabled visualization and interaction with these raster gridded map products that update daily and monthly, along with time series for exploration. Download of all these different products. So there's over 100 years worth of rainfall products at a monthly time scale, and over 30 years at daily time scales for temperature and rainfall products. And so we have a nice query interface that they can query and make different data packages for different date ranges of data that they want, and different product types of maps or station data and things like that, that they can either download through our interface, or they can choose and get an email and download the product later. So how are things going now? After 1 month of being released, we've had 2,500 visitors so far from 43 countries, and we've had 81,000 file downloads out of the data portal. So I think it's been relatively successful right now, and so we're pretty excited. For future work, we're going to add additional climate products. So evapotranspiration, solar radiation, I think, are some of the next ones we're going to be working on. We're going to be working with folks on API access. So we have some city and state entities, as well as some researchers that have already requested access that are interested in being able to interact with our services and our data for some additional products and dashboards that they're building. Integration of this tool for other decision support tools like drought and fire analysis and prediction. And then the community is coming in with requests for other ways to view some of the anomaly data, which wasn't released in our release a month ago. So that's all stuff that we're working on. So I just want to say thank you, everyone, for your attention and attending the talk. If you're interested, you can follow the project on Instagram or Twitter. Here is the URL. It's hawaii.edu/HCDP if you'd like to go visit it. And I'd like to thank funding from the National Science Foundation for our EPSCoR, which is the EKY Securing Hawaii's Water Future, as well as funding for the TAPIS framework. And thanks to the full team of folks here that helped make the product possible. There's a lot of climate scientists and other folks in our group that made this possible, as well as there's some cultural resources and some folks from the community that helped out with this. So at this point, I will take some questions.
If you have a question, feel free to unmute or type it into the chat. Well, thank you, Sean.
All right, thanks, everyone.
Is the next team ready?
Yeah.
Optimize terapixel scale processing of astronomical images. Please begin.
Okay, let's see. I think you can see the
I can see it now.
Okay. There we go. Okay, sorry. My name is John Good. I'm an astronomer at Caltech. We've been building image processing software for use with archives and any other data you've got for over 20 years now. And we've been collaborating with another group at USC who build workflow management software for operation on all sorts of scales, including the cloud and clusters and everything else. And recently we've been trying to scale this up to where we can deal with all sky mosaicing, build maps that have terapixel scale. I mean, it's like the sky is like 1 million pixels across or around. What we want to do is to be able to set this loose on an entire archive of images and have it process the whole thing efficiently and as cheaply as possible, which is the hardest part, on clouds like we're mainly concentrating on AWS right now. So we're using two data sets specifically. One is WISE, which was done 15 years ago or so here at Caltech, and is in 4 bands, covering the entire sky, but has a lot of issues with things like zodiacal dust, which at these wavelengths shows as a massive band of brightness across the sky. We want to try and take that out as much as possible. And also the and TESS, which is an ongoing project, not here, that is monitoring the sky, or in chunks at least, and trying to find exoplanets by watching transits. We've done, so I'm going to get into a minute, I'm going to get into how the workflow management software works. But they have tools that can be used from Jupyter Notebooks for building the workflow, for setting it up. Yeah. So the process of dealing with a workflow is you set it up first, you build what's called a directed acyclic graph that says, okay, here's the process. You can do this, and then you have to wait for this to happen before you can do this. And they manage the actual submission of specific processing tasks to different compute nodes. But setting it up is done beforehand. And they now have Jupyter Notebooks constructs that allow you to actually build the workflow and get it all worked out right. And then you can have it submitted to run wherever you have resources. We've done all sky processing ourselves using a local Slurm cluster. And we want to try and do this on like I said, mostly AWS. And we've also done a fair bit of work with on AWS with managing resources, with firing up, provisioning machines and turning them on, turning them off, to minimize the cost. If you leave machines running, you pay for it, even if they're doing nothing. But I suspect there's people here that know something more about that part of it than we do, and that's one of the reasons we're here. The two tools we're talking about are Pegasus from USC and our own Montage image software, imaging software. They're both open source. They run on multiple platforms. They're cross-compiled to work on Windows and things like that, though we don't normally do that ourselves. They're built into shared object libraries, so they can be run, they can be wrapped to run from Python. Pretty well documented, easy to use, given the complexity. And these two work very well with each other. We've been collaborating for more than 15 years. So Pegasus does the planning, it monitors the jobs as they run, and it's got a scheduler and all sorts of stuff. It works on, as I said, multiple platforms. So if you haven't used Workflow Manager before, they're very good for setting up processing jobs where you don't have to basically script everything and worry about moving data around and starting jobs. And one of the things they don't do very well in general is to deal with the starting and stopping of nodes. They were built in an era when you got access to something and you had the whole thing for a while. And so the whole idea of efficiently turning things on and off needs to be added. Though I suspect we'll probably have to add that in our planning, this part, the tools we build that they then manage. They do deal with having multiple copies of data if that's appropriate, with restarting jobs if they fail and all of that, which is very useful on some platforms. It's not usually that much of a problem on things like the cloud. This is an example of a very abbreviated DAG. For montage, very often you have a region of the sky, you've got hundreds, thousands. In the case of the Olsky, we have millions of images that all have to be reprojected. Overlaps between them have to be analyzed so that we can match the backgrounds, which is often a problem, and then co-added. In this, there's a choke point in the middle here where we have done all the differencing, and we need to do a sort of a global analysis. But that point isn't a problem for most of the time, because the preceding steps are usually fairly predictable in terms of the amount of time they'll take. And so we can manage to have a whole bunch of parallel stuff ending at about the same time. Do this quick modeling and then continue on, fan it out again. A more realistic DAG is this diagram over here that is totally unreadable. And in the lower left, we've got an example of the actual Jupyter notebook that was put together for creating the DAG that would run over there. Now we've run this on the Open Science Grid before now. Actually, Pegasus, the guys at Pegasus ran it just to test that the DAGs that we generated would work. And it was really great for what we wanted to do. But most people are going to have, some people can get access to this, but most people are going to have to use something like a commercial grid if they want to do this kind of work. So this was just an example of a relatively small job running on that grid. So the map here is an example of an Olsky, the kind of product that we can generate. This is in the infrared. It's a map of the entire sky. The center of the galaxy is middle left. And the large and small Magellanic Clouds, other galaxies, are showing down in the lower right. This was data. The data for this was taken back in 1983. We now have the resources to build this kind of interactive map. This actually is a product from CDS in France, where you can, if you make the right kind of map, they have software that will display it. You can scroll around, rotate this sphere, and zoom in. And in the case of the WISE data we were talking about, you can zoom in factor of, let's see, 2 to the 6th. And so you can get up fairly close. You can get down to tiny pixels, arcsecond pixels. Okay. What we want to do, and this is, if anybody here has some insight into this, we'd be very interested in talking, is we want to manage the resources. It's one thing to say, well, I will provision 200 processors and then start throwing things at them. But if your processing only needs that part of the time, and then part of the time it needs 10 processors and so on, and the intrinsic part of the task is to decide when to turn things on and off, when to clear out this storage, when to move this from here to here, and things like moving data from the cloud to your own local storage is actually very expensive. And so you need to plan all of that out. And that has to be part of the processing task. And so I haven't seen much in the way of write-ups on good ways to do that. Everybody pretty much does it themselves. So that's the main thing we're interested in adding to what we do in the near future. Okay, that's about it. Anybody have any questions?
So I have a question. Thanks for the great talk, John. So moving really to the cloud, which challenges do you think do you have to address? So we did see yesterday, for example, a talk about, you know, the different costs in clouds and everything. So is there something in place where you would say, oh yeah, we are monitoring that, or is it at the beginning more like a general technical challenge?
Yeah, the real technical challenge is kind of predicting that and controlling it. So yeah. If you know at a given time that you need these resources, fine, turn them on. But then as soon as you don't need them anymore, turn them off. Otherwise, you're using up all of your money.
Yeah.
And I haven't seen much in the way of that being incorporated into tools. I mean, Amazon's perfectly happy to have you have machines doing nothing. They get paid the same amount either way.
Yeah, thank you very much. Yeah, I know that it's really a big challenge. Yeah.
I think it's an area that deserves a lot more thought.
Definitely.
Okay.
John, I'm just wondering, have you looked into reserved instances on Amazon, on AWS?
Well, sure. But you know, there are plenty of ways to get cheaper versions of the same thing. I mean, you can use the spot market, for instance, if you don't care exactly when the thing finishes. But that's not the same thing as in a given situation minimizing the what you use at a given time.
Okay, thank you. Any other questions? All right, let's take a 4-minute break as the other team prepares. We'll come back at 11:45, and if there are any other questions in the interim, feel free to ask or put them into the chat. Ted, you look like you're ready to go. Okay.
Yeah, whenever I can just put my title screen up now, if that's okay.
Sure, sure. Okay, looks like there aren't any discussions or questions. Let's go ahead, Ted, if you're ready. Exceed GPUs, speed genomic analysis, and gene patterning. Go ahead.
Okay, hi, my name is Ted Liefeld. I am the software architect for the Mezerov lab at the UCSD School of Medicine, and I'm going to tell you how we're using the Exceed GPUs to speed genomic analysis in gene pattern. So there are a large number of executables already available for bioinformatics. Many of these are command line, so you could install them into your own environment with all their dependencies and maintain them that way. But that isn't making life any easier for a biologist who isn't and does not want to be a programmer or systems administrator. It also prevents you from easily sharing your analysis pipelines with people who may be on a different platform. Also, for compute-intensive analysis, such as assembly, alignment, or highly parametric methods, such as non-negative matrix factorization, you don't want to run them on your local laptop if you can avoid it. So to address issues like these, we developed GenePattern. GenePattern is an analysis gateway that manages the compute environments required for analysis, interfaces to high-performance compute systems, and maintains an analysis history and provenance to support computational reproducibility. Its goal is to provide an environment for reproducible integrative genomic analysis. This is the analytical interface to GenePattern, and a few examples of the ways in which you can use it to visualize different genomic data types. Available analyses in GenePattern include general machine learning approaches, bulk and single-cell RNA-seq analysis, cancer-focused tools, a suite of gene set enrichment analysis methods, and many other omics modalities. At a very high level, the GenePattern architecture looks something like this. Our biologists and bioinformatician users typically connect to GenePattern gateways through a web browser. We currently have 2 gateways available for public use, and there are other private instances hosted at universities, biotech, and pharmaceutical companies. After selecting an analysis and setting the input data and parameters in the GenePattern gateway, the job is dispatched to a compute node where an execution environment is set up. Data is provisioned into it, the analysis is run, and finally the outputs are collected and sent back to the gateway. The details of how this happens depend on the specific gateway. At the San Diego Supercomputing Center, the Expanse supercomputer provisions compute nodes, and jobs are run in Singularity containers or on the GPU partition. For our gateway hosted on Amazon Web Services, AWS Batch provides the compute nodes, and Docker containers provide the execution environments. Between these 2 public gateways, we typically see around 400 users running around 2,000 to 3,000 jobs in a typical week. GenePattern Notebook is an integration of the Jupyter Notebook environment with GenePattern. This gives you all the benefits of Jupyter with capabilities for bioinformatics analysis from the hundreds of methods available in GenePattern, plus additional functionality to make notebooks accessible to non-programmers. Using GenePattern notebooks, you can add any GenePattern analysis as a cell within a notebook without the need to write code. Data can flow seamlessly between GenePattern cells and Python cells. GenePattern notebooks can be added to any Jupyter or Jupyter Lab as a set of plugins, and we also host a publicly available Jupyter Hub at notebook.genepattern.org. Now, one of the analyses available in our GenePattern gateway is non-negative matrix factorization, NMF. And NMF is largely combined with the consensus clustering approach in GenePattern, where it's called Nmf Clustering. Let's take a look at what NMF and Nmf clustering are all about. Basically, NMF is a dimension reduction technique. In gene expression analysis, we typically have thousands of genes. This causes problems with achieving statistical significance, as well as difficulty in interpreting what we are seeing biologically. Therefore, it's common to use dimension reduction techniques to reduce the number of dimensions we have to deal with. NMF is an algorithm that can reduce high-dimensional data sets of tens of thousands of genes to a handful of metagenes, which are easier to interpret biologically. NMF takes an input matrix A and returns 2 matrices, W and H, and iteratively modifies them until their product is approximately equal to the A matrix based on a cost function. If A has n gene rows and m sample columns, then W and H will be n by k and k by m respectively. The factorization rank k is a value that's much less than both n and m. So let's take a moment to compare NMF to a faster and simpler dimension reduction technique, principal component analysis, or PCA. NMF provides a more natural way to cluster genes and samples because its matrices contain only non-negative values. By contrast, PCA provides an algorithmically simple way to reduce dimensionality, but the matrices must be orthogonal, which usually results in components with both positive and negative signs. So this means in PCA, gene expression may be negative. However, in biology, a cell cannot express less than 0 or none of a gene, which makes the biological interpretation impossible. So while NMF is more costly to compute, it provides a more intuitive decomposition of the data. So we use NMF to describe the tens of thousands of genes in a genome in terms of a small number of metagenes. Samples can then be analyzed by summarizing their gene expression patterns in terms of the expression patterns of the metagenes. The NMF algorithm may or may not converge to the same solution on each run, depending on the random initial conditions. If a clustering into K classes is strong, we would expect that the sample assignment to clusters would vary little from run to run. A single run of NMF can be thought of as an optimization problem that may get stuck in a local minima. So we evaluate the stability of clusters for a given rank K by performing many iterations of NMF with varied initial conditions. And then we look for the consensus clusters that are stable. In this example, we can see that the clusters of samples for K equals 2 and 3 are very stable, but as K increases, the clusters become less stable with the possible exception of that cluster at the bottom right of the figures. So we then use this information to select a best value of K based on another cost function, which is not shown here. And then this is used for the biological interpretation of the metagenes or subsequent analysis. Now, the problem with NMF is it is what mathematicians, and I am not a mathematician, call a non-convex optimization problem. This means it's not guaranteed to find a global minima, and the runtime scales polynomically with the size of the input matrix. Now, the size of gene expression data sets has grown hugely in the last 2 decades. In the late 90s, you would be lucky to find data sets with 100 or 200 samples. Today, you can find data sets that have over 300,000. So imagine what happens to the compute time when one of the dimensions goes up by 3 orders of magnitude and we're working in polynomial time. But it's also true that the analysis is primarily matrix operations, and there is a class of processor that has been developed to do these very quickly in other applications, the GPU. And it also happens that in 2015, researchers from the University of Madrid made a GPU implementation of NMF. And this was based on the same Brunet et al. Paper, an implementation that our old CPU-based NMF clustering is based on. So we used this as the starting point for a new, faster implementation to run on the Expanse GPU cluster at SDSC. So how much does this speed things up? Here we have a comparison of the runtimes of the CPU and GPU versions. Each of these data points represents the average of 100 runs of NMF clustering. The input sample sizes are artificially small because even for just 160 samples, the CPU-based version hits the 48-hour time limit we have for jobs. We can already see the effects of polynomial time, even with these small sample sizes. Now, a potentially confounding factor is the amount of memory available. The CPU runs were assigned 2 CPUs and 8 gigs of RAM each, while the GPU runs were assigned a single GPU with a much larger 186 gigs of RAM. So we did a bit more testing, rerunning smaller data sets on the CPU version with a quadrupling to 8 CPU and 32 gigs of RAM, and we found no performance impact. Similarly, we reran a few iterations with 3 GPUs and 300 gigs of RAM assigned, and again saw no performance impact. These small data sets are just too small for the additional memory to have made a difference. With the GPU-based implementation, we see a factor of 63 speed up with the biggest data set it could complete, about 80 samples. This is a bit less than what the Nmf GPU paper led us to expect, where they reported it was around 120 times faster. We think this is likely due to a couple of factors. First, the different hardware used, both CPU and GPU, on their tests in 2015 versus ours in 2022. But also, we see that the increase in time of the GPU implementation is still climbing more slowly than we would expect with 640 samples. So this might indicate that we are still seeing a contribution from startup overhead that is large compared to the actual computation time. We're continuing to work on our benchmarks, however, and hope to have a more definitive answer in the future. So in conclusion, the GPU-backed Nmf clustering is now available in beta on our gateway at genepattern.ucsd.edu. I should actually, as an aside, it's actually also now available on the AWS batch gateway. However, that delegates the run over to the UCSD version. This now makes it possible to explore small data sets quickly and permits the application of NMF to data sets larger than possible before. And a reminder, GenePattern and its analysis modules, including this one, are free to use and open source. Some future developments are still planned for this module. We would like to further explore the performance boundaries and specifically determine the approximate maximum size of a data set that's possible with our current compute environment. We also want to test the differences between dense and sparse matrices. A collaborator has a single-cell RNA-seq gene expression breast cancer dataset with 320,000 samples, or cells, that we would like to be able to apply this to. Also, the GPU code from Madrid supports MPI parallelization across multiple nodes and GPUs. We haven't tested this yet, but the underlying code has the plumbing in place already. And finally, we're going to be adding additional cost functions, starting with the Kullback-Leibler, or KL divergence. And with that, I think I have a couple of minutes left for questions.
If you have questions, feel free to unmute or put them into the chat.
Yeah, thank you very much for a great talk. So if you look at the different data and the simulations you run, then so can you also say maybe, so the experience you made with this, with the the increased performance, can you also relate that to additional data or to similar simulations that people can reuse what you have done?
Could you restate the question again? I'm sorry, I didn't quite catch that.
Oh, sorry. So you got a really nice, increase of performance, which is fantastic. We all know, so so with this performance comparison, do you have related research and cancer where you could get with similar cases a similar performance increase? Is that like having a class of different applications where you say, oh, you can use these our method also to increase your performance? Is that something?
Yeah, I guess there sort of is actually. There are two other labs, one on the East Coast at Johns Hopkins and another one also at UCSD with us, who are both also interested in using the GPU-backed Nmf for their analyses. So they're doing different things. One of them is doing like a gut microbiome data, whereas the Johns Hopkins people are also, I think, doing cancer research like we are.
Okay, cool. I mean, because this was really a nice increase.
Oh yeah, it's again, with the old Nmf, the CPU-based version, it really wasn't very useful for any modern data set. Like our data sets these days are usually 1,000 to 3,000 samples is the most common, and it's we just simply can't use it without the GPU.
Yeah, I totally agree. Yeah, cool.
Any other questions? Ted, thank you very much. Great talk. If the other team is ready, we can go ahead. Collaborative analysis and visualization of geospatial data using HasMapper Geo API. Is that Nathan? Are you ready? All right, go ahead.
Oh, hello. Thanks for joining. I'm Ian Park. I'm a developer at Texas Advanced Computing Center, and I'll be talking in behalf of me and my colleague, Nathan Franklin, on a project we're working on together. The talk will be about collaborative analysis of geospatial data using HasMapper and Geo API.
That's great. Thank you, Ian.
Yeah.
Go ahead if you're ready. You're a little early, but it's up to you.
Do you see the? Oh, sorry. Do you see the? Oh, do you see the slides?
Yes,
Okay.
the slides are I see them clearly, and they look great. Go ahead.
Okay. To give a brief background of this project, so Natural Hazards Engineering Research Infrastructure, NHERI, is a program funded by the NSF. And we're part of a team that's working on Design Safe, which is a portal gateway for researchers to run applications, upload and share, publish data sets for hazard research alongside their publications. The RAPID is a facility that focuses on field reconnaissance on natural hazards. They collect data in the field before or during or after disaster events like storms, earthquakes, and fires. And the collected data gets stored and shared within Design Safe for collaborative analysis and or publication. And as you can see, kind of like through the activities of the RAPID facility, there's a lot of field reconnaissance data in this form of research, which translates to geospatial data. So the main motivation for our project started from the RAPID facility needing a way to coordinate and visually represent the vast amounts of geospatial data they were collecting. And similar to what the Rapid team does, there are many other teams that upload geospatial data due to the nature of hazard research. So we have a lot of uncoordinated geospatial data stored in DesignSafe. So we wanted to come up with a solution to neatly coordinate and represent the data for visual analysis and to provide alongside the published data in publications. And in trying to utilize the data in DesignSafe, we realized that it was difficult to use existing GIS tools seamlessly on the web. So we needed a web-based tool that could support many geospatial formats, including things like LiDAR point clouds that are often not supported even in comprehensive desktop GIS software. So the goals for our project, first of all, is integration and utilization of the data on DesignSafe and linking the represented data with publication pipelines that DesignSafe provides. Second, we want to be able to handle large amounts of geospatial data sets with various formats. And third, we want to efficiently serve large LiDAR point cloud data sets, which, as I mentioned earlier, is difficult to find in existing mapping applications. And fourth, we wanted to create a collaborative workflow for coordinating and analyzing these data sets. So, so this is kind of the diagram of the general architecture. Each lighter, like inner border box represents different containers. So we use Kubernetes to manage these containers at scale. On the front end, we have HasMapper, so that's our main front end. We have an Angular app with a leaflet providing map functionality. And on the back end, we have Geo API. So, so it has the actual API application, which is a Python Flask application that handles requests. And we have a worker application using celery task queues combined with RabbitMQ message broker that allows us to import and process various geospatial formats from DesignSafe into Geo API and serve them in a web compatible manner. And we have a database with Postgres with PostGIS, which allows us to do like geospatial queries in our database. And beneath all of this, we mainly talk to DesignSafe through Tapas. So Tapas is the underlying API that allows us attack to utilize our infrastructure. It provides an abstracted way to do many powerful computational operations. And all tech portal gateways, including DesignSafe, we use Tapas. In HasMapper and Geo API in particular, we use it to access and download and upload files stored in DesignSafe and to link DesignSafe project systems to our own format. So, yeah. So the main functionality of HasMapper Geo API is first, we have a map. So these are the instances of the application. So you can think of something like a project or a document in other programs. These are meant to be collaboratively edited. So members of the map can simultaneously add, remove, or edit the content of the map. We have observable maps, which are maps, but then they're synced with the location path in DesignSafe. And this allows users from DesignSafe to dump data on folders as they're collecting something like reconnaissance data and would not have to manually import things into HasMapper. And we can automate that process. And we have public maps, which are read-only permalinks to maps that are shareable with anyone with the link without worrying about the map getting overwritten. Next, we have tight-knit integration with design-safe projects and publications interfaces. So you can display a list of maps in the projects. Kind of looks like this. So this is a design-safe project that has an associated map or two maps here. Yeah, and finally, as we mentioned earlier, as one of our goals, we support many geospatial formats, geotagged images, videos, GeoJSONs, tile server layers, GPS tracks, shapefiles, point clouds, and we're working on Street View assets as well through a service called Mapillary. Yeah, so here's some screenshots of the features. We have some working already and some in progress. So this is an example of 3 types of assets like GPS tracks, clustered image assets, and GeoJSON features. Next, we have kind of the Street View implementation using Mapillary. So yeah, so we can have like Street View images inside a HasMapper map. Next, we have point clouds that are rendered on the map. And I think this is Sydney. And 3D tile layers. So these are kind of things we're still working on. Not released yet, but yeah. Okay, so next, now I wanted to show you a real life use case of HasMapper. This material has been provided to us from the Rapid team. So the Marshall Fire was a historical fire that happened in Boulder, Colorado last year, December. It destroyed 1,000 homes. And so the Rapid team was deployed on site after the fire. They used drones to collect point cloud data and ortho mosaic images. And that amounted to like 100 gigabytes of compressed point clouds, LiDAR point clouds, and 250 gigabytes of ortho mosaic images. And these were all uploaded into HasMapper. And as a result, they were able to share it with other field researchers and have a coordinated representation of HasMapper for analysis and publication. And they said that the first place that HasMapper would be the first place for people to interact with data and see what data sets they want to download for their own research. So yeah, so that was really good to hear. And these are kind of the images that from their project, from the Marshall Fire that they've uploaded onto HasMapper. So the blue boxes are kind of the point cloud regions, and the green dots are clustered images that you can zoom into, and you can slightly see the orthomosaic geotiffs rendered underneath them. And this is what happens when you click on a point cloud at the moment. And you can later on see this in another tool we have called Poetry. So that renders these point clouds. And you can navigate around observing the data. Yeah, so the outcome of all of this was that yeah, so the Rapid team was able to share data with other field researchers. So there are plans now to upload to HasMapper for each NSF deployment from Gear and the Rapid team. Public HasMapper data would be shared alongside design-safe project data. So there'd be a formal way to kind of represent this. And they gave us an estimate of like 20 deployments a year. So that amounts to about 2 terabytes of data uploaded to HasMapper and design-safe. For future work, we're trying to figure out scaling. So we recently ramped up on a lot of usage. So we're making effort to adjust to scale. We're planning on working on optimizing and improving the scale. scaling of processing tasks, uploading, and just storage. We're trying to support more geospatial file formats because that's one of our strong suits. And we're transitioning to MapLibre or for WebGL utilization for modern and faster mapping features. And we, alongside the format support, we want our own tile server to be able to process and visualize data directly from DesignSafe. At the moment, we rely on external tile servers like ArcGIS to host like the GeoTIFFs, but we want that built in. So thanks for listening. I want to give special thanks to Michael Grilliot, Karen Dudinsky, and Jacqueline Besky from the Rapid team for working on the Colorado datasets. Also to Brad Wham, the principal investigator for Marshall Fires from the University of Colorado Boulder, and to Joe Myring, who is a former colleague who's no longer working with us, but contributed significantly to HasMapper and GeoAPI. And here are the links to our software repositories. They're all open source. We have the open API specs for GeoAPI and the link to the application itself. Let's take questions if we have time.
Thank you, Ian. If there are any questions, go ahead. Okay, well, thank you very much, Ian. Is the next group ready, Andrea and Julian? Distributed, okay. Distributed computing on the cloud for science gateways with Dusk. If you're ready, feel free to go ahead.
Okay, I'm gonna start screen sharing. I'm also going to put a link in the chat where you can find the slides and you can find the links. Okay, can you see my screen fine?
Yes, see it clearly. Go ahead.
Okay, very good. Let's start. So I'm Andrea Zonca. I work at San Diego Supercomputer Center. And today, together with my colleague Julian Chastang at UCAR, we're going to present how we've been using Dusk to provide users with distributed computing on the cloud, and specifically thinking about science gateways. So this talk is mostly for science gateway developers, and in the process of preparing this talk, I have created a series of tutorials where you can install all the different components of this setup on Jetstream to be able to have a setup like this configured on your account. So let's first of all start with our platform. So currently we're working on Jetstream 2. We just transitioned. We were using Jetstream 1 before. And the first two tutorials, you see the links here, are about deploying Kubernetes and Jupyter Hub. Okay, so let's take a look at the architecture. So we have our Jetstream. So Jetstream is an OpenStack cloud at Indiana University, and allows you to deploy a distributed system. So let's say, for example, that we have a number of virtual machines. And so first of all, we want to create a distributed system where, for example, we can provide Jupyter notebooks to our users. And so this is useful for science gateways, for example, to allow people to use the gateway through the Jupyter notebook, or to post-process the results of the gateway in a already prepared computational environment. And so, first of all, we install Kubernetes on those virtual machines so that Kubernetes can handle all of the services that we need to deploy the services, to capture login, to handle networking, to provide the resilience. So if any of the services dies, it can be restarted. And so Kubernetes is coordinating all of this environment, and inside Kubernetes, we can deploy our services. So our first service is Jupyter Hub. So Jupyter Hub is running inside a Docker container, inside a pod in Kubernetes. And when a user comes in, so they connect to Jupyter Hub, they authenticate, and then through the Kubernetes API, Jupyter Hub requests a computational environment to be deployed somewhere in the cluster. And so all the little details are hidden from us because, of course, Kubernetes is handling all the low-level stuff. And so, and then if we have multiple users coming in, they are also going to get their environment. And this is good for interactive computing, but sometimes we want to give our users more computational power. And this is where Dusk Gateway comes in. So Dusk Gateway is another service that we deploy alongside our Jupyter Hub instance on Kubernetes. So is composed by, has two components. So the proxy is just handling all of the necessary networking. And the most important service is the Dusk Gateway server that provides APIs so that the Jupyter Notebook users can connect to this server and to the Dusk Gateway API and request a Dusk cluster to be created for them. And so this, of course, goes through Kubernetes, and we have our scheduler created, just a private scheduler just for that user, and a bunch of workers. So in this example, we just have a couple of workers. And now the Jupyter Notebook user can connect to the Dusk scheduler and launch distributed jobs using the very high-level interface of Dusk, which from the user perspective is very easy to use, looks a lot like NumPy, but under the hood, you are actually driving computation on a distributed environment. So you have part of an array, for example, is on one worker, the other part on the other worker, but everything is handled automatically by Dusk. Okay, and another option to use Dusk in our in our environment is actually to provide the capability of using distributed computing to the Science Gateway itself. And so to provide an example of this, I've created a tutorial where I have a very simple gateway implemented in Flask, is 50 lines of code, that provides an API to launch jobs. So when a user connects to a specific URL, a job is created, and this job is a parallel job on our Dusk cluster, and then the outputs are saved on object store. So let's see here. So we have now we have our gateway, which is another service which is running in Kubernetes, and it has its own scheduler, which is dedicated to the gateway, and a few workers, in this case 3. And so when users are connected to the gateway, the job, instead of running inside the gateway, so if you have a computational job, is offloaded to the scheduler, and the scheduler connects to the workers, and then we have this parallel job executed in the workers. And to make the most use of this, of the cloud environment, we are also parallelizing the data output. So all the data that this gateway is producing is going to be directly saved to object store, and so that the workers can, in parallel, all of them connect to object store and create an output file, which is in a specific format, which is optimized for cloud computing, which is ZAR. And ZAR is basically made of chunks, and so each worker can independently write those chunks. And once these outputs are written to object store, then the user can post-process them from Jupyter Notebooks, or they are just available for future use. And I've provided a tutorial that goes through all of this and allows you to deploy a very simple prototype system based on this. Now we will switch to a specific case study, and Julian is going to talk about that.
Hello, everybody. Can you hear me okay?
Yeah.
Hello. Okay, great. Okay, hello, everybody. I'll now describe how I employed Andrea's work for a WRF data case study on the Unidata Science Gateway running on Jetstream 1. So back in December, I was approached by a Rutgers University professor to analyze and visualize some weather research and forecast WRF data coming from a climate change simulation. Because of the voluminous nature of the data, it could not be read into memory at once. So the goal was to use Xarray, the Xarray Python library, with a DAS cluster to rapidly analyze and visualize the data in a Jupyter notebook. The DAS cluster was a challenge to build, not on account of Andrea's work, but I had a tremendous amount of trouble coordinating the Conda environments. But once that work was done, everything worked really well. I was able to build a 4-worker, 16-task stream cluster. And by the way, you can find the Docker files associated with this cluster, as well as the Jupyter notebook at that QR code. Next slide, please. Okay, this is simply a screenshot of that notebook, making a wind speed calculation and then plotting those data, and it is employing that DAS cluster that I just described. And it may be hard to discern, but those are wind speeds being plotted above the North American continent. Next slide, please. This is a screenshot of the DASK dashboard in action that demonstrates all the 16 task streams that are running in parallel. I start off the notebook with an embarrassingly parallel small calculation just to demonstrate to myself that the cluster is working as expected. That's what that small, very thin first vertical line is on the left of the task stream. Yeah, exactly where Andreas is pointing. And afterwards, the notebook proceeds with its analysis and visualization. And you can see that all the pistons are firing, all those task streams are going forward. Okay, so I just want to say that I actually just got this working this week on Monday, so I have not many results to present beyond that. I can confirm that running it with one task stream takes about 1,000 seconds for the notebook to run, and running with 16 task streams takes about 300 seconds to run. So we're seeing a benefit in the parallelization, which is great, but obviously I would like to collect a lot more metrics than just that. And that's where the future work will be done. I aim to collect better data and metrics about different chunking and parallelization schemes. And oh yeah, thank you, Andrea. I forgot to mention next slide. Yeah. And just to repeat myself, yeah, I aim to collect better data and metrics about different parallelization and different chunking schemes. And I want to apply to different data sets with my colleague at Rutgers. And I really look forward to working on Jetstream 2 and the large instances there. And that is what I have at this time.
Very good. Thank you, Andrea and Julian. Are there any questions?
Hi, Andrea. This is Chunhan. I have some question for you. You say like a Kubernetes cluster inside. You are saying like a Dask cluster is running implemented both together, or so I'm just computing that. Like, this means like within Kubernetes the cluster, then Dask like cluster is installed, deployed, right? Something.
Yeah, so basically the Kubernetes cluster is on top, and the Dusk cluster is inside Kubernetes. So basically each of the Dusk service, so the Dusk cluster is done by the scheduler and the workers, and they are other pods. Okay, so there is the Dusk Gateway, which is deployed. Dusk Gateway is an actual project. So if you, if you Google for Dusk Gateway, you can find their documentation. Okay, so Dusk Gateway is actually, you see, is deployed on top of Kubernetes, and so it's a service which is running as a pod on Kubernetes, and when someone connects to that pod, can request other pods to be created. And so one pod is running the scheduler, and then you can have any number of pods running the workers. Okay,
I see.
And yeah, and then when the user, and so with Kubernetes you can configure it to have some number of CPUs per worker, some amount of memory per workers, and so you have your distributed cluster of Dusk workers that are running as pods inside Kubernetes.
Yeah, pod inside. Okay, I got it. Yeah, thanks.
Yeah,
I think there was just a question, Andrea, in the chat about whether if this runs on OpenStack infrastructure. And the answer is yes, of course.
Yeah. So Jetstream is running is an OpenStack cloud, and so what we do is we install Kubernetes on top of OpenStack. Okay, and Kubernetes itself is connecting to the OpenStack APIs. Okay, for example, we want to provide storage to our users. So when a person connects for the first time with Jupyter Notebook, we want to provide him with some storage, and that's where Kubernetes talks to OpenStack to have an OpenStack volume being created, and then that OpenStack volume is attached to the virtual machine where the user is running. Okay, so there is interconnection between Kubernetes and OpenStack. Okay, and currently we are deploying Kubernetes using KubeSpray. Okay, another option would be to have actually Kubernetes deployed with Magnum, which is the OpenStack service. And I think that's not ready yet for Jetstream 2. And as soon as that's ready, I will want to try that, because the great thing about using Magnum is that we can provide automatic scalability. So having the cluster automatically grow, the Kubernetes cluster automatically grow when we have more demand for resources and shrink when there is less demand. For now, the deployment with KubeSpray is static. So it's always the same number of virtual machines.
Very good. Well, thank you very much, Andrea and Julian. Everyone, this concludes the lightning talk sessions. Thank you very much.